Electromagnetic waves are found everywhere, and there are many different types. When you microwave your lunch, you are using electromagnetic waves. Your skin becomes sunburned because of a different type of electromagnetic wave. An X-ray of a broken bone is still another example of how an electromagnetic wave can be used. No matter what type of electromagnetic wave, they will all travel at the same speed through space. When we talk about the electromagnetic spectrum, we are essentially including all of the different types of electromagnetic waves. We have radio waves, microwaves, infrared waves, visible waves, ultraviolet waves, X-rays, and gamma rays. The many different types of electromagnetic waves are defined by their wavelength and frequency. Wavelength is simply the measure of the length of one complete wave, in meters, and is represented by the Greek letter lambda. Notice that radio waves can be as large as several magnitudes in length, while gamma rays can be unbelievably tiny. Frequency is the other defining property and is a measure of how many waves pass a given point in 1 second. Frequency is labeled with hertz, and 1 hertz describes 1 wave per second. The electromagnetic waves between the wavelengths of about 400 nanometers and 750 nanometers is the part of the electromagnetic spectrum that a human eye can perceive. We call this the visible spectrum, or just visible light. The wavelength of the wave is interpreted by our brain as a specific color. On the left end of the scale, we have red light with a relatively high wavelength of 750 nanometers. As the wavelength gets smaller, the color changes to orange and then yellow, green, and blue. At the far right of the spectrum, the light becomes violet at 400 nanometers. But because of this higher wavelength, the frequency is quite a bit lower. Think about a wave passing you by on the dock. If the waves are larger, fewer of them are going to be able to pass by you in a given time frame, whereas waves with a smaller wavelength will pass by more quickly and therefore have a higher frequency. This is kind of interesting because if we multiply those two labels together, we get meters per second, which we know is velocity. We have determined that the speed of an electromagnetic wave is 3.0 times 10 to the 8th meters per second. So we can draw the conclusion that this is equal to the frequency of the wave times its wavelength. Because the speed of the wave is constant, this relationship allows us to calculate either the frequency or wavelength when one of them is known. So calculate the wavelength of a 1530 kHz AM radio signal. We are given the frequency, but note that it is in kilohertz, not just hertz, so we'll need to account for that. And we always know C, so this is simply a matter of plugging in our numbers and solving for an unknown. And we get a wavelength of 196 meters. This is nearly 2 football fields in length, so quite a big difference from our visible light.